It is my enormous pleasure to introduce Vann McGee from the Massachusetts Institute of Technology, who is our scholar of consequence for this year. Vann, as I just learned that Vann got an MA from Chapel Hill before getting his PhD in the group of logic and methodology of science at UC Berkeley. Then, after some years at Rutgers, in the mid-90s, you went to MIT, where you still are.
I was in Arizona.
You were. It's very hard to find out things about you online.
Every winter, this time of year, I'm at intense regret. Tenure at the University of Arizona. Tenure. Why did I leave?
So I missed that. Apologies. All right. And in 2016, you were elected member of the American Academy of Arts and Sciences. And so much for quick biography. But so the Scholar of Consequence Award that we give away every year goes to a scholar is to honor a scholar who has, this is what it says, made significant contributions to the field of logic. And for Professor McGee, there are too many of those than I will be able to list, even if I take more time than I should with this. So let me just quote from your website, Ben. You say there that your work displays a wholesome concern for truth and rationality, and combined with a pathological preoccupation for paradox. That is a fabulous characterization of what you're doing. Your first book, Truth, Vagueness, and Paradox, an essay on the logic of truth, I think displays that, because the book, which was incredibly influential and won the Johnsonian Prize in Philosophy, which is given out by the Journal of Philosophy in 1988, that takes us from certain semantic paradoxes and take us through some of the most important theories of truth, so Bartarski, Kripke, Pfefferman, and others. And you combine these problems that we get in these approaches with the question of how are we dealing with vagueness, until we end up in the last chapter with a proposal for a semantics for natural language, for English. So all the way from paradox to semantics for whole speed. And that is just your first book. Something that we pay very much attention to, it's very important to us, and that's not often get managed, is that you are also one of the very early on provided a free textbook in logic that you made freely available to everyone. And that is certainly stuff like that promotes the study of logic, that doesn't take money out of students' pockets, and still provides first-class text to learn, which is something I think is not mentioned often enough. So you did that as well. But of course, you're most well known for your work on truth, both in the philosophical and the formal realm. You work on reference in the philosophy of mathematics. You worked in multiple areas of logic. So comes to mind as conditionals, probability, conditional probability, provability logic, computability / recursion theory. And some of the main contributions, although as I said, I cannot mention all, is that you repaired two defects with Tarski's approach to logic. His approach to consequence, and also his invariance criterion for logical constants. We provided fixes for shortcomings there. We work unrestricted quantification on the categoricity of categoricity results for arithmetic he showed us how to use the notion of an open schema to provide categoristic results in a pre-proper second order formulation of the theory. You work in plurals, and you also gave us delightful things like the Wombat disjunction. And of course, the infamous, notorious, I should say, account examples from modus ponens. So all of this, and as I said, I haven't mentioned all of it, I think is more than enough to I don't have a handout, so I can't read all the time what you're talking. Thank you very much. So today, oh yeah, of course, how could I forget? Terrestrial Logic. Vann, thank you very much.
So, thank you very much for the generous introduction. I don't mind a bit that it was excessive. Thank you very much for having me here, and thank you very much for coming here today. Grateful. A common practice among philosophers, you might regard it as a character flaw, is this: you find a book or an article that you really like, and there's one or two paragraphs that you disagree with, and you focus all your attention on that one or two paragraphs. So I'm going to do that. And the article is Russell's masterly 1927 paper, Vagueness, whose principal point is that vagueness is everywhere in human language and thought. So any idea that questions about vagueness can be safely set aside because they occur at the periphery of language while we get a grip on what's going on in the center of town, that sort of methodology is misguided. So he goes so far, vagueness is everywhere, he says. And he goes so far as to say, even the logical words like or and not are vague. He thinks this because he thinks of them as them as truth functions. There's functions that take truth values, either true or false. Truth values, and he thinks they're defined by the truth tables, and those definitions aren't precise because the words true and false aren't precise. So he concludes, all traditional logic habitually assumes that precise symbols are being employed. It is therefore not applicable to this terrestrial life, but to an imagined celestial existence. This, I want to say, is going too far. So there are two strategies for making out the connections between semantics and inferential practices. There's the semantics first approach, which starts with truth conditions and then looks for rules of inference that are reliably truth preserving. And there's the rules of inference approach, which starts with the rules of inference and looks to find a theory of truth that fits those inferential practices. So, exemplar of a semantics first approach is Tarski's theory. Tarski starts with the truth conditions. Now, anything that you might come up that would look like a theory of truth is likely to be difficult and sure to be controversial. But Tarski says you can give the truth conditions for particular sentences very easily. The truth conditions are given by the T sentences, which follow the paradigm snow is white is true if and only if snow is white. Now, there's a word of caution. A sentence isn't either simply true or simply false. It's true or false in a language, in a context. So Tarski's original English language example of a T sentence was, it is snowing is true if and only if it is snowing. Well, it is snowing is true at a time and place if and only if it's snowing then and there. So okay, Tarski was working entirely with formal languages. He didn't think his methods were applicable to natural languages. And he thought of formal languages the way model theorists think of formal languages. Sentences are sequences of entities that are misleadingly called symbols that are formed according to certain syntactic rules, and that they need have no connection at all with anybody's speech practices. So Tarski's program started with truth conditions given by the T sentences. And then he wanted to get from that to an explicit definition of truth by looking at how the truth conditions for complex sentences are determined by the semantic values of the simple parts of the sentences. And there was an obstacle, namely, complex sentences aren't typically built up from simple sentences. And the technical fix was to recognize that open sentences, that sentences are typically built up from simple open sentences. Where an open sentence is like a sentence only can have three variables. And so, and it could give a compositional theory of how open sentences are satisfied by functions assigning values to the variables. So the base was the atomic formulas who got disquotationally a variable assignment sigma satisfies x loves y if and only if sigma of x loves sigma of y. And then the satisfaction conditions for compound sentences were given compositionally. A variable assignment satisfies a disjunction if and only if it satisfies one or both disjuncts, and so on. And finally, a sentence that is a closed sentence, an open sentence without free variables, is true if and only if it's satisfied by every variable assignment. So Tarski was looking almost exclusively at mathematical languages, which vagueness isn't much of a concern. Once we leave the math department, there's a central conflict that we get irreconcilable but nearly irresistible answers to two questions. The first questions is what are the conditions under which a given sentence is true? And the second one is, how does it come about that the sentences have these truth conditions? And okay, the answer to the second question has got to be speaker usage. What else could it be? Sentences don't have their meanings innately or inherently. They don't have natural meanings the way a red sky at dawn is said to mean stormy weather ahead. Credulous' idea that words were given their first meaning by a more than human power has won few adherents. And the idea that semantic properties of expressions of the language are just a free-floating, brute, inexplicable fact has even less appeal. So it's got to be that the semantic values of expressions are given to them by speaker usage, and there's a conflict when you start to look at vagueness. Because usage doesn't determine. And well, okay, the picture is that usage determines the conditions under which a sentence is true, and then facts about what the world is like, which aren't in general dependent on usage, determine whether those conditions are met. That's the general picture, but it's troubled with vagueness. Okay, a sentence like Carlos is rich might be neither true nor false because it's semantically defective. That would happen in a situation when there isn't a unique, conceptually salient individual named Carlos. But if it's the referent of Carlos is uniquely determined, then Carlos is rich is true if the speaker practices in using the word rich make it correct to affirm of people in Carlos's financial situation that they're rich. And Carlos is not rich is true if speaker usage term makes it correct to deny of people in Carlos's situation that they're rich. And the problem is that usage doesn't determine a down to the last penny and stick of gum partition separating the people of whom it's correct to deny that they're rich and the people of whom it's correct to affirm that they're rich. So one wants to say that, well, if Carlos is one of these borderline cases, he doesn't meet the usage-defined conditions under which to say he's rich is true, so Carlos is rich isn't true, and he doesn't meet the usage-defined conditions under which it's correct to deny that he's rich. So Carlos is not rich isn't true, and treating falsity as truth and negation. Carlos is rich isn't false. So we get the conclusion that Carlos is rich. Neither Carlos is rich nor Carlos is not rich is true, but that conflicts with the answer to the first question. Answer to the first question, well, the obvious answer to the first question was given by the T sentences. And the two T sentences, Carlos is rich is true, if Carlos is rich. Carlos is not rich is true, if and only if Carlos is not rich, together entail that Carlos is rich is one or the other of Carlos is rich, Carlos is not rich is true. So we got this conflict. If we're going to recognize vagueness, the natural way to recognize vagueness is to say that if Carlos is a borderline case of rich, neither rich nor not rich applies to him. And assuming Carlos has a definite referent, that means that Carlos is rich is neither true nor false. That's a natural thing to say, but if you say that, that conflicts with the T sentences. So think about this Sorites paradox. You have a long sequence of tiles very gradually changing from red to orange, so gradually that speakers can't detect any difference in color between adjacent tiles. So red's a vague term, so they're going to be, yeah, because there's got to be a red tile adjacent to a not red tile. And on the natural assumption that a tile is red, even though it's correct, call it red, that means there has to be a tile that it's correct to call red adjacent to a tile that it's correct to call not red. But how can that be? What makes it correct to call the tile either red or not red is speakers' practices in using the word red. And how can there be anything about speakers' practices that makes it correct to call one red and the next one not red when speakers can't detect any difference in color between the adjacent tiles? So, a key observation is to, more than anyone else, to Bosman Frossen, is that it's possible to give up by valence the semantic thesis that every sentence, every non-defective sentence is either true or false, and uphold classical logic. There's a cost to doing that, means giving up some of the T sentences. Another cost is it means giving up the compositional grounding relation that we naturally expect, where what makes a disjunction true is the truth of one or more of the disjuncts, and what makes a conjunction true is the truth of both the conjuncts. If Carlos is either red, if Carlos is red or handsome is true, what makes it true is either or both of Carlos is rich being true, or Carlos is handsome being true. However, Carlos is rich or not rich can be true without either disjunct true. So what makes Carlos is rich true, if it is facts about Carlos, is facts about Carlos and his financial situation. What makes Carlos is rich or not rich true has nothing really to do with Carlos's financial situation. It has to do with the meaning of the words true and false. Now, and looking at the meanings of words true and false, look at the meanings of the words true and false, so one understands, okay, how are these words used? And the use that stands out so prominently is that they are used in deductions. That use is so preeminent as to make the audacious claim loosely attributed to Gensen that the meanings of the logical words is given by the rules of inference, at least plausible. And I want to claim that Gensen's audacious proposal is correct, and in fact, the rules of inference determine the semantic values of the logical operators precisely. The key to getting that result is an observation of Kreisel and Charles Parsons about the role of the principle of mathematical induction in arithmetic. Peano arithmetic, as Peano formulated it, had a principle of mathematical induction that said for any class R, if 0 is a member of R, and if the result of adding 1 to a member of R is a member of R, then every natural number is a member of R. The advantage of that theory is that on a proper understanding of classes, it gives a categorical characterization of the natural number system. Any two models that fit that characterization are isomorphic. The disadvantage is that it requires a prior understanding of classes. Nowadays, what people refer to as Peano arithmetic is instead take the induction axiom to be the schema, take it not to be an induction axiom, but an induction axiom schema obtained from Peano's axiom by removing the initial quantifier for all R and calling any sentence you get by replacing R with an arithmetical formula and prefixing universals to bind the resulting free variables, an induction axiom. The advantage of that theory is that it's self-contained. The disadvantage is that it isn't categorical or even complete. Kreisel and Parsons suggest a third way out. Namely, we regard the axiom schema as open-ended. So usually it's understood that a formula language of arithmetic is what you can substitute for R. The Parsons and Kreisel's proposal is, no, we can suppose we allow substitution not just of arithmetical formulas, but of formulas of languages that we could get by extending the language of arithmetic. The idea is that take an extension of the language of arithmetic, substitute formulas from that, open sentences from that language for the schematic letter, and that still gives us an induction axiom. Okay, say substitute. So, okay, the idea is we're going to add new predicates to the language and allow them to appear in induction axioms. That's the idea, but you can't really use a syntactic test for what you're going to count as adding a new predicate to the language, because there's no prohibition against introducing a new term in the language that behaves syntactically like a predicate and stipulating that a sentence containing that new term is true if only if the term occurs in an odd number of times. So you can't have a syntactic criterion. You need the new predicate has to behave semantically like a predicate does. But to get the categoricity result, we don't need to say anything about in general about what a predicate does. It'll be enough to say what a precise predicate does. And for that, the answer seems pretty clear. The answer is a precise in-place predicate picks out some intervals as the things that satisfy the predicate. So what gets the categoricity result is that for any individual, for any individuals, there's an extension of the language of arithmetic in which there's a precise predicate that picks out those individuals, and that any induction axiom that you get either in the language of arithmetic or extension of the language of arithmetic is true in all the intended models of counting. Those criteria let us show that any intended model, those criteria let us show that the only intended models of the language of arithmetic are the standard models. You can do the same trick with real analysis, applying, taking the least upper bound principle to be open-ended. That's something one really needs for applications, because you need that to get from the thesis that the mathematical formulas accurately describe the cannonball's trajectory to the conclusion that there's an instant at which the trajectory reaches its highest point, at which the cannonball reaches its greatest height. Okay, so that's the background. The idea is to apply that idea to logic by treating the rules of logic as open-ended. So they're going to maintain not only for our current languages, but for new languages. We might add to our current languages by adding new precise predicates. And we're doing an inference first approach. We're supposing the rules and asking, okay, if we've got the rules, what do those tell us about truth conditions? And the rule for disjunction tells us that the disjunction of two open sentences is the strongest open sentence with the property that every variable that assigns the first disjunct and also that it's satisfied by every variable assignment by first that satisfies the first disjunct, and also by every variable assignment that satisfies the second disjunct. And that tells us that a disjunction, a variable assignment satisfies a disjunction if and only if it satisfies one or both disjuncts. The negation of an open sentence is the weakest open sentence. Negation of open sentence 5 is the weakest open sentence with the property that no variable assignment satisfies both it and phi, and a variable assignment satisfies the negation of phi if and only if it fails to satisfy phi. So we get the expected semantics, or the textbook semantics for the sentential calculus operators. For the quantifiers, well, their words like all, every, and some have non-logical uses. If you say everyone is going to be at Julio's opening, I don't mean everyone in the whole world is going to be at Julio's opening. Certainly not that every entity in the universe is going to be at Julio's opening. I mean that everybody in the in crowd is going to be at the opening, and being a member of the in crowd is not a logical notion. When we write for all x, x is mortal as a way of expressing the idea that every human being is mortal, we are applying a tacit restriction that says the only values that the variable is allowed to take are human beings. There's a logical use of all and or that you get by not imposing any restrictions on what the values of a variable be, and allowing use of the quantifiers to be governed by the logical rules alone without any further constraints, and treating the laws for universal quantification that way. We see that for all x phi is the weakest open sentence with the property that, okay, so the weakest open sentence without reoccurrences of x with the property that every variable assignment that satisfies it satisfies phi. And a variable assignment satisfies for all x phi if and only if every variable assignment that agrees with it, except possibly in the value it assigns to x, satisfies phi. Similarly, we get a characterization of the existential quantifier. Furthermore, the rules uniquely identify the identity operation as sigma satisfies x equals y if and if sigma of x is equal to sigma of y. So this is, okay, I've not been saying this, and I should have. In each case, we're talking about when we talk about, say, the disjunction of two. I'm always talking about disjunction of two open sentences formed from precise predicates. If the components are precise, then if the components of a disjunct, if the disjuncts are each precise, then if the disjunction each have uniquely determined conditions of satisfaction that are explicit and exhaustive, then the disjunction does too. So a test for vagueness is that if you have a sentence like Carlos is rich, that's neither true nor false. And if Carlos has a uniquely determined referent, the explanation why Carlos is rich lacks a truth value must be the imprecision of the word rich. Conversely, more or less, if there are borderline cases of rich, then it will be possible to produce, or at least envisage, a sentence that's neither true nor false, in which every part of the sentence other than the word rich is precise. Applying that idea to the logical operators, if an open sentence, if you have a open sentence formed using the logical operators, and every component of that open sentence other, wait, sorry, of, yeah, if you have a sentence formed using the logical operators, and if if you have a sentence formed using the logical operators that's neither true nor false, the reason that it's neither true nor false is that one or more of the non-logical terms that occur in it are vague. So all the logical terms that are occurring in it are vague. The whole sentence is going to be precise. And if the sentence is imprecise, so the sentence is imprecise, it's because one or the other of the logical terms that occurs in it is vague. In that situation, we want to say, well, if the sentence is imprecise, the reason for the imprecision is the imprecision in the predicates and not any imprecision in the logical operators. And that's why I want to get to the conclusion that the logical operators are precise. Now that gives us a pretty good account of how the logical operators interact with precise predicates. With imprecise predicates, we're going to have sentences that have a status in between truth and falsity, and we'll have objects with a status in between satisfying the predicate and satisfying the negation. And the intermediate statements can have come closer. One of two individuals with the intermediate status, one can come closer to satisfying the predicate than another. If Carlos is better off financially than Sochi, then Carlos satisfies Rich as well or better than Sochi satisfies Rich, even if neither of them outright satisfies either Rich or not Rich. And if Carlos and Sochi are precise names, then Carlos's Rich will be as true or truer than Sochi is Rich, even if neither of them is either outright true or outright false. So sentences can have a status in between truth or falsity, and these intermediate statuses degrees. Why should we care about the degrees? I mean, we wouldn't a simple true, false, neither dichotomy give us exactly what we want? Okay, we have an immediate interest in truth because we aim to assert and accept things that are true. That immediate interest gives us an immediate interest in degrees of truth. If Carlos is Rich is a degree of truth greater than the degree of truth of Sochi is Rich, then the conditional, if Sochi is Rich, Carlos is Rich, is outright true. So, So, okay, so we want to look at, okay, there are two kinds, we want to look at, okay, our program is starting with rules of inference and trying to get an appropriate semantics. So the rules of inference are of two kinds. They're direct rules like modus ponens and ex contradictione quadruped, which lets you tell us that certain conclusions can be drawn from certain premises. And they're indirect rules like conditional proof, reductio ad absurdum, and cut, which tell you that if you've carried out a certain deduction, that entitles you to carry out a certain further deduction. So if you've derived psi from gamma together with phi, you're entitled to derive if the conditional if phi then psi from gamma alone. Okay, that's doesn't quite pin down what the rule is. If you've derived psi from gamma together with phi, well, exactly what principles of reasoning are you allowed to use in deriving psi from gamma together with phi? Well, as long as we're staying within the pure predicate calculus, the answer is clear, the textbooks all agree. The consequence relation is the smallest one that contains the direct rules and is closed under the indirect rules. But possible conflicts arise when you're looking at rules of inference, when we're thinking about employing principles of reasoning that are reliably truth preserving, but that they are reliably truth preserving isn't guaranteed just by the rules of logic. So, for example, mathematical induction. And then we maybe have conflicts. Fine introduces a definitely operator by saying that definitely phi is going to be true if phi is true, definitely phi is going to be false if phi isn't true. That means that the inference from phi to definitely phi is truth preserving. Well then, says fine, we can assume phi, conclude definitely phi, then conditionalize to get the conditional if phi then definitely phi without any premises. Do the same thing with not phi, and we conclude that either definitely phi or definitely not phi. In other words, we conclude by vagueness. Fine says, okay, what that means is that if you want to deny bivalence, then you're going to have to restrict conditional proof. So what the lesson we thought we got from Van Prossen, that you can have classical logic without bivalence, turns out to be misleading at best, since yes, the classical rules are upheld so long as we confine ourselves to the quiet streets and manicured lawns of the first order predicate calculus. But once we go beyond, outside those pampered domains, we find that conditional proof is no longer allowed to us. So what we get is an innervated form of we get a form of classical logic, but it's an innervated form, which can no longer count on once you leave the domain of pure logic. So we need to restrict conditional proof. Okay, from an inferentialist point of view, inference rules first. semantics later, that's not an option. We're given the rules of inference, and conditional proof is one of them. And our task is to find a semantics that fits. We're given the rules of inference, and we need to find an appropriate semantics. So, and conditional proof is one of the rules. So, we need a better account of what inferences you're allowed to make in going from gamma, the premises gamma union phi together with psi, beyond the one that, other than the one phi gives, namely the good inferences are ones that are truth preserving. The alternative account we need is not hard to find. The good inferences are going to be ones that are degree of truth preserving. So if you can derive psi from phi, then you need to be assured that the degree of truth of psi is at least as great as the degree of proof of phi. So, now a bivalent setting, the two standards, truth preservation and degree of truth preservation, are indistinguishable, but you do distinguish them when you don't have bivalence enough. So if our standard of good argument is a good argument, it's one that's truth preserving, that means that we need to restrict conditional proof, reductio ad absurdum, and cut. Whereas if we adopt a more rigorous standard that requires of a good proof, not only that if the premise is true, the conclusion's true, but also that if the premise is nearly true, the conclusion is true or nearly true. If that's our standard of good argument, well, Fine's counterexample to bivalence, or counterexample rather to conditional proof, no longer goes true because the inference from phi to definitely phi is not degree of truth preserved. So we can hold suppose we okay, so think about our sequence of tiles, sequence of 100 tiles fading, glacialating from red to orange. Now we can prove that the disjunction, either the first tile is the last red tile, or the second tile is the last red tile, or dot, 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 or the 99th tile is the last red tile. On the other hand, because speakers are unable to distinguish any difference in color between adjacent tile, there's no end for which the sentence, the nth tile is the last red tile, is true. So the inference from the nth tile to 37 is the greatest prime is truth preserving. And that means if we have proof by cases, the rule of inference that says you can derive a certain conclusion from a disjunct if you're able to derive it from a disjunction if you're able to derive it from disjuncts. If we have proof by cases, we're able to prove that 37 is the greatest prime. But 37 isn't the greatest prime. So and Tim Williamson conclude that in order to, if we're going to renounce bivalence, we have to also give up proof by cases, saying that they're guided by Williamson's slogan, validity is necessary preservation of truth. I would want to propose a different slogan, validity is necessary preservation of degrees of truth. And that preservation, that more rigorous slogan that's harder for an inference to be valid enables us to uphold additional proof by cases. Okay, the rules. Okay, I mean, this an inferentialist program. We're assuming taking the rules for granted, and the rules tell us that. Okay, we're taking the rules of inference for granted, and we want a story about the degrees of truth that fits with that story. So the rules tell us that the degree of truth assigned to a disjunction is the least upper bound of degrees of truth assigned to disjuncts. Tells us that the degree of truth of a conjunction is the greatest lower bound of the degrees of truth assigned to the conjuncts. And so the degrees of truth